based on the equation that we wrote at the end of last video, we want to set everything equal so that the s squareds are equal, the s's are equal, and the 1's are equal. So on the left, I've got s squared times 0 should be the same as my a plus b that's times s squared. Then for my, maybe I'll write right here that that came from s squared. Then for my s-type terms, I've got 0 on the left, and on the right I have 3b plus c. And for my constant type terms, I've got 26 on the left, and that should be equal to my 4a plus 3c. So we're going to start solving this. For my top equation, 0 is equal to a plus b. That's going to give me that b should be equal to minus a. And then I'm going to go ahead and substitute that into my second equation. So instead of 0 is equal to 3b plus c, that's the same as 3 times minus a plus c. And that's going to tell me that c is equal to 3 times a. I'm just trying to get everything in terms of one variable so I can solve for it, and then we'll be able to plug everything back in. Taking that down to my third equation, I've got 26 is equal to 4a plus 3c, but now I know that that's 3 times 3a, or I guess like that. Oops. 3 times 3a, or 9a. So that means that I've got 26 is equal to 9 plus 4 is 13a, or a is equal to 2. Then if c is equal to 3 times a, that means c is equal to 3 times 2 is 6. And if b is equal to minus a, that means that b is equal to minus 2. So now I know that if I have 6 over s plus 3 plus 26 over s plus 3 times s squared plus 4, that's the same as 6 over s plus 3 plus a over s plus 3, so 2 over s plus 3, plus bs plus c, which is minus 2s plus 6 over s squared plus 4. So everything that I did in the middle here was just so that I could turn my messy fraction into something that looks more like things I can take Laplace transforms of. And I'm going to simplify this even more a little bit. So my 6 and my 2 combined, they have the same denominator, so I can just add them up. That becomes 8 over s plus 3. And I'm going to go ahead and split up this fraction here so that I have something that only has s on top, like I'm used to seeing for my cosine type terms, and something that only has a number on top, like I'm used to seeing for my sine type terms. Remember, we can split up the numerators, we cannot split up the denominators. And then finally, we will actually be able to compute this inverse Laplace transform. I need to switch slides for that to happen, so please pause if you're still writing. But my inverse Laplace transform just becomes inverse Laplace of 8 over s plus 3 minus 2s over s squared plus 4 plus 6 over s squared plus 4. And here we're going to go and do like we had at the very start of this video, where we use linearity and special constants to make this look like something we can take the Laplace of. So I'm going to pull out my 8 here. I'm left with L inverse of 1 over s plus 3. I'm going to pull out my 2 and be left with L inverse of s over s squared plus 4. And then for this last term, since this is one of those cases where I've got 4 on bottom, so that's 2 squared, I need to have 2 on top. So we're again gonna have this case where we split up 6 into 3 times 2, and we pulled the 3 out, so only the part that makes Laplace work is inside. And that's going to be one of our sine type functions. In the middle here we also have k equals 2, but since there's an s on top, it's one of our cosine type functions. And then this first term is one of those s minus a problems, but since we have s plus 3, that actually means that a is minus 3. We've got minus 3 gives us plus 3. And I guess I didn't write up above, but I'll do it here. We're also going to be using that L of e to the at is that 1 over s minus a. So taking our inverse Laplaces, first we apply that property. We've got L inverse of 1 over s plus 3 must be e to the minus 3t, because that's our at. Minus 2, that L inverse is just a regular cosine of kt, but for us k is 2. And then for that last, we've got a regular sine of kt for k equal to 2. And then that's our answer. What's cool with the Laplace transform problems when we're solving initial value problems is that because we introduce our initial condition when we compute our derivatives, we don't have unknown constants at the end. We just end up getting the solution after we take that inverse. So it's kind of nice, it's all built in. We're going to do one more example just to get more practice with this. So I'm going to pause and move over to the next video.